Integration by parts is another method to take an antiderivative, specifically for things that you're taking the product of. Since we don't necessarily have a product rule for integration, we have to figure out another way to work with it. I'm going to go through a short proof of where the rule for integration by parts come from. And what we're going to do is start with the product rule for derivatives. First thing I'm going to do is I'm going to go ahead and define two functions. I'm going to let u be f of x and let v be g of x. Okay, so instead of using f of x and g of x, we'll just use u and v. So the product rule says if you take the derivative of u times v, it's u times the derivative of the second plus derivative of the first times the second. So this is just the product for derivatives, which we already know. Now I can kind of rearrange the terms. I'm going to go ahead and give this by itself. So if I do that, I end up with this. Right? Just move this over to the other side, isolate this and this, and I just moved terms over to the other side. Now, I'm going to go ahead and integrate both sides. So anything I do to one side, as long as I do to both sides, it's the same thing. So I'm going to go ahead and take the antiderivative both sides. And if I do that, notice what happens to this piece right here. The antiderivative and derivative are inverse operations, so you're really left with just uv. And then this one, there's really nothing I can do with, so I'm going to leave it like that. Okay, I'm going to do one last step. I'm just going to rewrite v prime as dv and rewrite u prime as du. So integral of u dv is uv minus the integral of v du. Okay, this is the rule for integration by parts. And basically, it's just a manipulation of the product rule for derivatives. And what it says is if you have two things being multiplied, where one is the original function u, and you're multiplying with the derivative of another function, the rule says you take u times v minus the integral of v du. Now, the key to this problem is figuring out what piece in the problem is u and what piece in the problem will be dv. So if you look at this first example, there's two functions you could possibly deal with. You've got x, you've got e to the 2x. So one piece is your u, the other piece is your dv. Now some problems you can interchange it and you can still get to the answers, but some problems if you don't, then you're going to be going in circles. The way that I'm going to have you guys pick your u is use this little acronym, okay? And this is what you are going to do to pick your u. So this is the hierarchy that we're going to use. So you're going to look for logs first. That's your L. Your I is going to stand for inverses, so inverse trig functions, arctangent, arcsine, etc. Your A is going to be any type of algebraic function, so x squared, x cubed. Your T is going to stand for trig functions. Your E is going to stand for exponential functions. So this is going to be the hierarchy that you are going to use to pick the u, and then everything else in the problem is going to be your dv. Okay, I'm going to go ahead and put that over there. So let's look at this problem here. So let's go through and try to figure out what our u is going to be in this problem. These are the two pieces that you have. So I don't have any logs. I don't have any inverses. The next letter is A, which stands for algebraic. Notice that this is an algebraic piece. So your u is going to be x. That means everything else in the problem will be dv, which is your e to the 2x dx, right? So the idea is we want to make it fit this form so we can use this rule. So your u, so this is my u, so this is my dv. So now this fits this rule. Once you have that, then I have to figure out what the right side is going to be. Now, in order to come up with the right side, you will need to figure out what du is. Du is just the derivative of x, which is 1 dx. And then you will also need to figure out what v is. If dv is e to the 2x, v is the antiderivative of it. So remember, when we do the antiderivative, we need that whole reciprocal idea. So your u here is 2x, du is 2, so we need that reciprocal. So your v is 1/2 e to the 2x. Now, once you have this, we're going to go ahead and just plug into our formula. So we have something in the form u dv. So integration by parts says the antiderivative is going to be uv. I'm going to put the 1/2 here, minus the integral of v, and I'm going to pull the number out in the front, du. Now notice your answer still has an integral in the answer, but now that should be something that you can do pretty easily. The antiderivative of e to the 2x is 1/2 e to the 2x, so really this is going to become 1/4 because you have another 1/2 e to the 2x, and then we'll put that constant of integration at the end. So the antiderivative of this is all of this. Okay, let's try another one. So look at number 2. So notice again, you've got two pieces you can possibly work with. You've got x, you've got secant squared. So I'm going to use this hierarchy, this LIAT hierarchy, to figure out my u first. So L is logs, there's no logs. I is inverses, there's no inverses. A is algebraic. Notice I do have an algebraic piece again, which is x. So that means everything else in the problem has to be dv. So that means secant squared has to be dv. So we need to figure out what du is, which is 1 dx. And the antiderivative of secant squared is going to give me tangent. So now we have something in the form u dv. The antiderivative of u dv is, using this rule that we just came up with up here, is u times v minus the integral of v du. And now we should be able to integrate the tangent of x. We have a rule for that. It's negative ln of cosine of x, so this becomes plus ln of cosine of x plus c.